Tonight, we're going to witness the end of our galaxy, not in some distant theoretical sense, but a collision that's already in motion, a cosmic train wreck that began millions of years ago and cannot be stopped. Right now, at this very moment, a galaxy containing 1 trillion stars is hurtling toward us at 250,000 miles per hour. It's called Andromeda, and it's on a direct collision course with the Milky Way. This isn't science fiction, this is gravitational destiny. The light you see from Andromeda tonight left that galaxy 2.5 million years ago, back when our ancestors were just learning to walk upright. And every second since then, Andromeda has been getting closer. The countdown has already begun. Before we dive into this cosmic collision, if you find yourself fascinated by the universe and our place in it, a quick like or subscribe would really help this channel grow. It's a small thing, but it makes a huge difference for me. Now, let's begin. Let's start with what we know about our own galaxy, the Milky Way. You've probably heard that it's big, and it is big. The Milky Way stretches about 100,000 light years from one edge to the other. That's a distance so enormous that light itself, traveling at 186,000 miles per second, takes 100,000 years to cross it. Inside this vast spiral structure, we have somewhere between 200 billion and 400 billion stars. The exact number is difficult to pin down because counting stars in a galaxy you're inside of is like trying to count all the trees in a forest while standing in the middle of it. Our sun sits about 26,000 light years from the galactic center, tucked into a minor spiral arm called the Orion Spur. We're not at the center of anything special. We're in the suburbs of the galaxy, in a relatively quiet neighborhood where stars aren't too densely packed. This location has been good for life. It's allowed Earth to exist in relative peace for 4.5 billion years, giving evolution the time it needed to produce complex life, and eventually us. The Milky Way is a barred spiral galaxy. This means it has a central bar-shaped structure made of stars, with spiral arms extending from the ends of the bar. If you could somehow view our galaxy from above, you'd see this beautiful pinwheel shape with arms of bright young stars, gas, and dust spiraling outward from a dense, central bulge. At the very center sits Sagittarius A star, a supermassive black hole with a mass of about 4 million times the mass of our sun. For most of human history, the Milky Way was everything. Ancient people looked up at that band of light stretching across the night sky and created myths about it. The Greeks thought it was milk spilled by Hera. The Norse believed it was the path to Valhalla. Chinese astronomers called it the Silver River. We didn't know it was a galaxy, a vast island of stars separated from other such islands by enormous gulfs of empty space. That understanding only came in the early 20th century. Before that, many astronomers believed the Milky Way was the entire universe. Andromeda itself had been observed for over 1,000 years. The Persian astronomer Abd al-Rahman al-Sufi described it around the year 964 as a small cloud in his Book of Fixed Stars. The fuzzy spiral shapes astronomers could see through telescopes, objects they called spiral nebulae, were thought to be clouds of gas within our own galaxy. The question of whether these spiral nebulae were part of the Milky Way or separate island universes became one of the great debates in astronomy. In 1920, astronomers Harlow Shapley and Heber Curtis formally debated the issue. The answer came 3 years later, when astronomer Edwin Hubble proved otherwise. Using the new 100-inch telescope at Mount Wilson Observatory, Hubble identified individual stars in what was then called the Andromeda Nebula. By measuring the brightness of a particular type of variable star called Cepheid variables, he calculated that Andromeda was far too distant to be part of the Milky Way. This was a revolution in human thought. In one stroke, Hubble had expanded the known universe enormously. The Milky Way wasn't everything. It was just one galaxy among many, perhaps billions. And Andromeda wasn't a nebula within our galaxy. It was an entirely separate galaxy, a vast island universe in its own right. Now let's talk about Andromeda, our future collision partner. The Andromeda Galaxy, also known as Messier 31 or M31, is the nearest large galaxy to the Milky Way. It sits about 2.5 million light-years away. That sounds far, and it is far by any human standard. If you could somehow travel at the speed of light, it would take you 2.5 million years to reach Andromeda. But in cosmic terms, 2.5 million light-years is practically next door. Andromeda is larger than the Milky Way. It contains approximately 1 trillion stars, more than twice what our galaxy has. It's also more massive overall, with a larger dark matter halo extending far beyond its visible stars. If the Milky Way is impressive, Andromeda is even more so. It's one of the most massive galaxies in our local region of the universe. You can actually see Andromeda with your naked eye on a clear, dark night. It appears as a faint smudge in the constellation Andromeda, just northeast of the Great Square of Pegasus. What you're seeing is the combined light of 1,000 billion stars, blurred together by the enormous distance. The light entering your eye tonight left Andromeda about 2.5 million years ago. The entire history of the genus Homo has played out during the time it took that light to reach us. Andromeda has its own supermassive black hole at its center, significantly more massive than the one in the Milky Way. Estimates suggest it has a mass of about 140 million solar masses, roughly 35 times more massive than Sagittarius A star. This difference in black hole size tells us something about the different histories of these two galaxies, the different mergers and accretions they've experienced over billions of years. Here's what's remarkable. Despite being 2.5 million light-years apart, the Milky Way and Andromeda are not sitting still. They're moving toward each other, and they're moving fast. The first hints of this came in 1912, when astronomer Vesto Slipher measured the spectrum of light coming from Andromeda. When he analyzed the light, he noticed something unusual. The spectral lines, the fingerprints of different elements, were shifted towards the blue end of the spectrum. This blue shift meant that Andromeda was moving toward us, not away. This was surprising because most galaxies show a redshift, meaning they're moving away from us as the universe expands. But Andromeda is different. It's close enough that its motion toward us overcomes the expansion of space. The gravitational attraction between our two galaxies is stronger than the cosmic expansion trying to push them apart. Modern measurements using the Hubble Space Telescope and other instruments have refined our understanding of this motion. Andromeda is approaching the Milky Way at a speed of approximately 110 kilometers per second, which is about 250,000 miles per hour. That's incredibly fast by human standards. At that speed, you could travel from New York to Los Angeles in about 36 seconds. But space is big. Even at 250,000 miles per hour, the journey from Andromeda to the Milky Way takes billions of years. The two galaxies have been approaching each other since long before Earth existed. they'll continue approaching for billions of years more before they finally meet. The question astronomers asked for decades was whether the collision would actually happen. You see, knowing that Andromeda is moving toward us isn't enough to predict a collision. You also need to know the sideways motion, the tangential velocity. If Andromeda has enough sideways motion, it could swing past the Milky Way, missing us in a cosmic near miss. Think of it like two cars approaching an intersection. Even if both cars are heading toward the intersection, they won't necessarily collide. It depends on the exact timing and angle of their approach. One car might pass through the intersection just before or after the other. For years, astronomers couldn't measure Andromeda's sideways motion precisely enough to know for certain. The galaxy is so far away that its apparent motion across the sky is incredibly small. It took the exceptional precision of the Hubble Space Telescope, observing Andromeda over multiple years, to finally nail down the answer. In 2012, a team of astronomers led by Roland van der Marel at the Space Telescope Science Institute announced their findings. By measuring the positions of individual stars in Andromeda over a 7-year period, they detected the galaxy's sideways motion for the first time. And the result was striking. Andromeda appeared to be headed almost straight for us. A collision seemed highly likely. However, more recent research has added complexity to this picture. Studies incorporating data from the Gaia spacecraft and accounting for the gravitational influence of the Large Magellanic Cloud and the Triangulum Galaxy suggests the probability of a direct collision may be closer to 50%. The galaxies might merge completely, or Andromeda might deliver a glancing blow, or in some scenarios, they might even miss each other entirely. The outcome depends on precise measurements that astronomers are still refining, but even a near miss would be transformative. Everything we know about the Milky Way, every star we can see, every constellation that has guided human navigation for thousands of years would be affected by such a close encounter. And if the collision does occur as many models predict, the galaxy that has been our home for the entire history of life on Earth will cease to exist in its current form. Let me explain why this collision is likely to happen by talking about the gravitational forces at work. Gravity is the weakest of the 4 fundamental forces, but it has infinite range and always attracts. This makes it the dominant force on cosmic scales. Every object with mass attracts every other object with mass, and that attraction never stops, never reverses. The Milky Way and Andromeda are both massive objects. Each contains hundreds of billions of stars, vast clouds of gas and dust, and enormous halos of invisible dark matter. This dark matter is crucial. The visible matter we can see, the stars and gas, makes up only a small fraction of each galaxy's total mass. Most of the mass is in the form of dark matter, which extends far beyond the visible boundaries of each galaxy. When we account for dark matter, the Milky Way's total mass is about 1.5 trillion solar masses. Andromeda's total mass is similar, or perhaps slightly larger. These two massive objects have been gravitationally influencing each other since they first formed billions of years ago. The gravitational force between them is pulling them together. This force has been acting for billions of years, slowly but relentlessly accelerating each galaxy toward the other. The closer they get, the stronger the force becomes, because gravitational force increases as distance decreases. Right now, the two galaxies are still far apart, and the gravitational force is relatively weak, but it's constant. It never stops. Every second of every day, Andromeda is being pulled toward us, and we're being pulled toward Andromeda. This has been happening since the beginning, and it will continue until the two galaxies finally merge. The local group plays a role in this story as well. The Milky Way and Andromeda aren't alone. They're the two largest members of a collection of about 50 galaxies called the local group. This is our cosmic neighborhood, a gravitationally bound structure about 10 million light-years across. Most of the local group's galaxies are small dwarf galaxies, tiny collections of a few billion stars or less. The Large Magellanic Cloud and Small Magellanic Cloud, visible from the southern hemisphere, are examples. These dwarf galaxies orbit the larger galaxies, bound by gravity to the Milky Way or Andromeda. The third largest galaxy in the local group is the Triangulum Galaxy, also known as M33. It's about 60,000 light-years across and contains roughly 40 billion stars. Triangulum orbits around Andromeda and may play a role in the upcoming collision. Simulations suggest it could merge with the Milky Way Andromeda system either before, during, or after the main collision. The entire local group is gravitationally bound. This means the galaxies within it will never escape from each other. Unlike more distant galaxies, which are being carried away by the expansion of the universe, the galaxies in the local group are close enough that gravity overcomes expansion. They're bound together, destined to interact and eventually form a single large structure. This gravitational binding is why the Andromeda encounter is so likely. It's not a random chance event. These two massive objects have been influencing each other since they first formed, billions of years ago. They've been drawing closer ever since, and the most probable outcome is that they will eventually merge. Let me give you a sense of the timescales involved. The universe is about 13.8 billion years old. The Milky Way formed about 13 billion years ago, not long after the Big Bang in cosmic terms. Earth formed about 4.5 billion years ago. Complex life appeared on Earth perhaps 600 million years ago. Humans have existed for maybe 300,000 years. The Andromeda collision will occur in about 4 to 5 billion years. That's a long time by human standards. Civilizations rise and fall in mere centuries. The entire history of human existence is a blink of an eye compared to 4 billion years. Whatever humans become, if we still exist in any recognizable form, will have changed so dramatically that we can't possibly imagine it. But 4 billion years is not that long on cosmic scales. The sun will still be burning then, though it will be nearing the end of its life. Earth will still exist, though it will be much hotter as the sun gradually brightens over time. Life might still exist on Earth, though it will have changed enormously over billions of years of evolution. And when we look out at the night sky 4 billion years from now, if anyone is looking, they'll see something remarkable. Andromeda won't be a small smudge of light anymore. It will dominate the sky, a vast spiral stretching across the heavens, visibly larger than anything our ancestors ever saw. It will be obvious, unavoidable, a cosmic presence that changes the very nature of the night sky. The collision itself won't be instantaneous. It will unfold over hundreds of millions of years, a slow-motion cosmic dance that transforms both galaxies completely. But once it begins, there will be no going back. The Milky Way as we know it will be gone forever. Understanding this collision requires understanding how galaxy collisions work in general, because the Milky Way-Andromeda collision isn't unique. Galaxy collisions happen throughout the universe. They've been happening since galaxies first formed, and they continue today. Astronomers can observe colliding galaxies at various stages, giving us a window into what our own future holds. When galaxies collide, individual stars almost never actually hit each other. This might seem counterintuitive. After all, we're talking about hundreds of billions of stars in each galaxy. Surely some of them must collide, but the distances between stars are vast compared to the sizes of stars themselves. Our nearest stellar neighbor, Proxima Centauri, is about 4 light-years away. If the Sun were the size of a golf ball, Proxima Centauri would be another golf ball about 1,000 kilometers away. Stars are tiny points separated by enormous gulfs of empty space. When galaxies merge, these tiny points pass through the vast spaces between each other. Computer simulations of the Andromeda collision show that the probability of any two stars actually colliding is essentially zero. Out of the combined trillion-plus stars in both galaxies, perhaps none will physically touch. But the galaxies themselves will be profoundly transformed. Even though individual stars don't collide, the gravitational forces during the merger will reshape everything. Stars will be flung onto new orbits. Gas clouds will be compressed, triggering massive bursts of star formation. The beautiful spiral structures of both galaxies will be torn apart and eventually destroyed. Astronomers have observed many examples of colliding galaxies throughout the universe at various stages of their mergers. These observations, combined with sophisticated computer simulations, allow astronomers to predict what the Milky Way Andromeda collision will look like. We can simulate the gravitational interactions between billions of particles representing stars, gas, and dark matter. We can run these simulations forward in time, watching the collision unfold over billions of virtual years. The results are both beautiful and violent. The collision will be a cosmic spectacle unlike anything humans have ever witnessed. And it's coming, whether we're ready or not. The first scientific prediction of the Andromeda collision came surprisingly early. In 1959, astronomer Erich Holmberg conducted a remarkable experiment. Unable to simulate the gravitational interactions with computers, which were primitive at the time, Holmberg used light bulbs to represent stars and photocells to measure the light. Since both light and gravity follow an inverse square law, decreasing with the square of distance, he reasoned that light intensity could simulate gravitational force. By moving light bulbs around on a table and measuring the forces, Holmberg was able to model galaxy interactions. His work showed that galaxies could experience dramatic transformations during close encounters. Though his specific predictions for Andromeda were limited by the technology of his time, he pioneered the field of galaxy interaction studies. Modern simulations use supercomputers to track the motions of billions of particles. These simulations have become increasingly sophisticated, incorporating not just gravity but also the dynamics of gas, star formation, and feedback from supernova explosions. The results consistently show that the Milky Way and Andromeda will undergo a dramatic merger, transforming both galaxies completely. One thing these simulations make clear is that the merger won't happen in a single pass. The two galaxies will fall toward each other, pass through each other, swing out to a great distance, and then fall together again. This dance will repeat several times over hundreds of millions of years before the galaxies finally settle into a single structure. Each pass will transform the galaxies further. Stars will be scattered onto new orbits. Gas will be compressed and heated. The spiral arms will be stretched and eventually destroyed. What emerges at the end will look nothing like either of the original galaxies. This is the likely fate of the Milky Way. The galaxy that has been our home for all of human existence, for all of Earth's history, for billions of years of cosmic evolution, will probably be completely transformed. Whether we experience a direct collision, a glancing blow, or a near miss that merely distorts both galaxies, the encounter will reshape our cosmic neighborhood. The gravitational dance between these two massive objects has been unfolding since the beginning of time, and the approach is already in progress. Right now, at this moment, the gravitational force between the Milky Way and Andromeda is accelerating both galaxies toward their eventual meeting. This cosmic dance has been unfolding for billions of years. Understanding the structure of both galaxies helps us predict how the collision will unfold. The Milky Way has several distinct components. There's the thin disk, where most stars, including our Sun, reside, orbiting in relatively circular paths. There's the thick disk, an older population of stars on slightly more elliptical orbits. There's the central bulge, a dense concentration of old stars surrounding the supermassive black hole. And there's the halo, a diffuse spherical region containing old stars and globular clusters. Surrounding all of this is the dark matter halo, extending far beyond the visible galaxy. Dark matter makes up about 85% of the Milky Way's total mass. We can't see it directly, but we can detect its gravitational effects. Without dark matter, the outer regions of the galaxy would be flying apart. The dark matter holds everything together. Andromeda has a similar structure, though on a larger scale. Its disk is bigger. Its bulge is more massive. Its dark matter halo is more extensive. When the two galaxies collide, their dark matter halos will interact first, long before their stellar populations touch. The interaction between dark matter halos is actually what drives the early stages of the collision. Dark matter doesn't collide in the usual sense because it doesn't interact through the electromagnetic force. It can pass through itself and through normal matter without any friction, but it does feel gravity. As the halos approach and interpenetrate, their gravitational fields distort each other, affecting the motions of everything within them. This dark matter interaction is invisible to our telescopes, but crucial to how the collision unfolds. Simulations that include dark matter produce very different results from simulations that only include visible matter. The dark matter provides the gravitational scaffold that shapes the merger. So let's journey forward in time and watch what happens as these two cosmic giants draw closer over billions of years. Because the collision isn't something that happens suddenly. It's a gradual process, a slow-motion cosmic ballet that unfolds across timescales almost impossible for human minds to grasp. Today, as you listen to this, Andromeda sits roughly 2.5 million light-years away. If you went outside tonight and looked toward the constellation Andromeda, you'd see a faint glow in the darkness. That's the combined light of over 1,000 billion suns, so distant that they blur together into a smudge smaller than the full moon. But Andromeda's getting closer. Every second, the distance shrinks by about 110 kilometers. That's about 68 miles per second. By the time you finish listening to this script, Andromeda will be about 400 kilometers closer than when you started. Not much, given the vast distance involved, but it adds up. Let's do the math. At 110 kilometers per second, Andromeda closes about 3.5 billion kilometers every year. That's roughly the distance from the Sun to Neptune and back. Every single year, Andromeda moves that much closer. Over 1 million years, the distance shrinks by about 3.5 quadrillion kilometers. Of course, these numbers don't mean much in terms of what you'd see. The distance to Andromeda is so enormous that even after 1 million years of approach, it would still appear virtually identical in the sky. The human eye couldn't detect any difference. But the change is real and is cumulative. Over billions of years, it transforms everything. Let's jump forward 1 billion years. Earth is now 5.5 billion years old. The sun has brightened considerably, making Earth uncomfortably warm. Life may still exist, but it's struggling. The oceans have begun to evaporate. Complex life on land may be extinct, retreated to the seas, or adapted in ways we can't predict. If any intelligent beings still exist and look up at the night sky, they'll notice something different. Andromeda is closer now, noticeably larger in the sky. It's still far away, still over 1 million light years distant, but it's no longer that faint smudge their distant ancestors knew. It's bigger, brighter, more obviously a galaxy. The Milky Way hasn't changed much yet in terms of structure. The spiral arms still exist. The sun still orbits the galactic center. But sensitive instruments would detect the faint gravitational tug from Andromeda, a subtle distortion in the orbits of stars at the outer edge of the galaxy. The approach has begun to have measurable effects. Let's jump forward again. 2 billion years from now. Earth is now 6.5 billion years old. The sun is approaching the end of its main sequence life. It's significantly hotter and brighter than today. Earth may be uninhabitable by this point, its oceans boiled away, its surface baked by the increasingly luminous sun. But look at the sky. Andromeda is remarkable now. It's grown dramatically, stretching across a significant portion of the night sky. The spiral structure is clearly visible to the naked eye, the graceful arms pinwheeling across the heavens. It's no longer a faint smudge. It's obviously, undeniably, a galaxy, and it's getting closer. The gravitational effects are stronger now. The outer regions of both galaxies are beginning to feel each other's pull. Dark matter halos, those vast invisible cocoons that surround each galaxy, have begun to overlap. The interaction is subtle, but it's real. Stars at the edges of each galaxy are being slightly perturbed, their orbits beginning to change. 3 billion years from now. We're getting close to the main event. Andromeda now dominates the night sky. It's larger than any astronomical object humans ever saw, stretching across dozens of degrees of sky. From a dark location, the galaxy's spiral arms would be visible in glorious detail. Rivers of stars punctuated by bright nebulae and dark dust lanes. The gravitational interaction is now obvious. Tidal forces, the differential gravitational pull that acts on different parts of an extended object, have begun to distort both galaxies. The outer spiral arms are being stretched, pulled toward the approaching galaxy. Some stars at the very edge of the Milky Way have been stripped away entirely, forming faint streams that extend toward Andromeda. This is the beginning of the tidal tail phenomenon. When galaxies approach each other, the side facing the approaching galaxy feels a stronger gravitational pull than the far side. This differential force stretches the galaxy, pulling material outward. The effect creates long streams of stars, the tidal tails that we see in colliding galaxies throughout the universe. Let me explain tidal forces in more detail, because they're crucial to understanding galaxy collisions. You're actually familiar with tidal forces even if you don't realize it. The ocean tides on Earth are caused by tidal forces from the moon and sun. The moon's gravity pulls on Earth, but it pulls more strongly on the side of Earth facing the moon than on the far side. This differential pull creates a stretching effect. The oceans bulge outward on both the near side and far side, creating the high tides we experience twice daily. The same physics operates on galactic scales, just much more dramatically. As Andromeda approaches, it pulls more strongly on the near side of the Milky Way than on the far side. This creates a stretching effect that elongates the galaxy. Stars on the near side are accelerated toward Andromeda. Stars on the far side lag behind. The result is a distortion of the galaxy's shape. 3.5 billion years from now, these tidal distortions are significant. Both galaxies have been stretched into elongated shapes, their once perfect spirals now visibly warped. Long tidal tails extend from each galaxy, bridges of stars reaching toward each other across the shrinking void. The approach is accelerating now. Gravity grows stronger as distance decreases, following an inverse square law. At half the distance, the force is 4 times as strong. At 1/4 the distance, the force is 16 times as strong. The closer the galaxies get, the faster they fall toward each other. Something else is happening as well. Gas clouds in both galaxies are beginning to respond to the gravitational disturbance. Gas behaves differently from stars in a galaxy collision. Stars are like marbles rolling past each other, unaffected unless they happen to pass extremely close. But gas clouds can collide, can compress, can interact in ways that stars cannot. As the galaxies approach, their gas begins to pile up in certain regions. The leading edges of the galaxies, the regions facing each other, experience compression. This compression triggers something remarkable: the first wave of collision-induced star formation. Star formation occurs when gas clouds become dense enough to collapse under their own gravity. Normally, this happens in spiral arms, where density waves compress the interstellar medium. But in a galaxy collision, the compression is much more dramatic. Vast regions of gas that were too diffuse to form stars suddenly squeezed into dense knots that begin to collapse. 3.5 billion years from now, astronomers would observe bright regions of star formation appearing in unexpected places. Not just in the spiral arms, but also in the tidal bridges connecting the two galaxies. New stars are being born in the space between the galaxies, formed from gas that was pulled out by tidal forces and then compressed by the collision. These new stars include many massive blue giants, the kind of stars that burn hot and bright and die young. Their blue light illuminates the gas around them, creating vast emission nebulae. The space between the galaxies begins to glow with the light of newborn stars. 4 billion years from now. We're very close now. Andromeda fills a huge portion of the sky. On one side of Earth, you'd see the familiar band of the Milky Way stretching overhead. On the other side, you'd see Andromeda. Equally impressive, the two great spirals facing each other across a shrinking gulf. The tidal distortions are extreme. Neither galaxy looks like it did billions of years earlier. The spiral arms have been pulled and stretched into complex shapes. Stars have been flung onto chaotic orbits. The once orderly rotation of both galaxies has become disordered. Gas is pouring out of both galaxies along the tidal tails. Some of this gas is falling into the space between the galaxies, where it collides with gas flowing from the other direction. These collisions heat the gas to millions of degrees, causing it to emit X-rays. The intergalactic space glows with high-energy radiation. Star formation has intensified dramatically. Both galaxies are now starburst galaxies, forming stars at rates 10 or 20 times higher than normal. The night sky is filling with new stars, brilliant blue giants born from the compressed gas of the collision. Many of these stars will live only a few million years before exploding as supernovae. But while they live, they light up the cosmos. The supermassive black holes at the centers of both galaxies are still far apart, but they're being affected by the gravitational chaos. Gas is beginning to funnel toward them, falling inward along increasingly crowded pathways. The black holes are starting to feed more actively, growing brighter as they consume more material. Active galactic nuclei, the brilliant cores of galaxies powered by feeding supermassive black holes, are among the most luminous objects in the universe. As the Milky Way and Andromeda approach, their black holes may begin to flare up, becoming active nuclei that outshine all the stars in their host galaxies combined. Let's pause here and consider what this means for our solar system. Because Earth is part of this story too. 4 billion years from now, the sun is old. It's been burning for 8.5 billion years, and it's nearing the end of its main sequence life. Even before that, the increasing luminosity makes Earth increasingly inhospitable. During the approach phase, before the actual collision begins, the solar system experiences relatively little direct effect. The tidal forces that distort the galaxies act on scales of thousands of light years. On the scale of a single star system, they're negligible. The sun continues its orbit around the galactic center, taking its planets with it, though the gravitational influence of Andromeda gradually perturbs that orbit over billions of years. What changes for Earth is the sky. The constellations that humans knew are gone, of course. Constellations are temporary patterns formed by nearby stars, and over millions of years, those patterns dissolve as stars move. The sky 4 billion years from now would be unrecognizable to us, even without the Andromeda collision. But with Andromeda looming, the sky is transformed in a more dramatic way. One hemisphere of the sky is dominated by this approaching galaxy, a spiral so large and bright that it affects how dark the night can be. The zodiacal light, the faint glow from dust in the solar system, is overwhelmed by the glow of Andromeda. True astronomical darkness becomes harder to achieve. 4 billion years, give or take a few hundred million. That's when the first contact occurs. That's when the edge of one galaxy first touches the edge of the other. That's when the merger truly begins. But let me be clear about what first contact means. It doesn't mean stars collide. As I mentioned earlier, stars are so far apart that actual stellar collisions are incredibly rare. What first contact means is that the dark matter halos, those vast invisible envelopes surrounding each galaxy, begin to interpenetrate. The stars at the outer edges of each galaxy find themselves passing through regions populated by stars from the other galaxy. Imagine you're on a planet in one of these outer regions. For billions of years, you've watched Andromeda grow larger in the sky. Now, something remarkable happens. New stars appear in your sky, stars that weren't there before. They're not being born from collapsing gas clouds, they're simply arriving, traveling from Andromeda into what was once purely Milky Way space. The night sky becomes richer, more populated, more crowded with stars. The two stellar populations are beginning to mix. Meanwhile, the gas interactions intensify. Gas from both galaxies collides in the overlap region, shockwaves propagating through the interstellar medium. These shockwaves compress the gas, triggering even more star formation. The merger region begins to blaze with the light of newborn stars. the gravitational dynamics become increasingly complex. Stars that were on stable, predictable orbits find their paths altered by the gravitational field of the other galaxy. Some stars are flung outward, accelerated to high velocities, and ejected entirely from both galaxies. Others fall inward, drawn toward the increasingly massive central region where both galaxies' cores are located. This is the beginning of violent relaxation, a process by which a gravitationally bound system settles into a new equilibrium after a disturbance. The regular, ordered motion of stars in spiral galaxies gives way to more random, chaotic motion. Stars no longer orbit in neat circles or ellipses. They plunge through the merge system on complex, irregular paths. The approach phase teaches us something profound about the nature of time and change in the universe. From a human perspective, 4 billion years is an eternity. It's almost impossible to grasp such a timescale. If you tried to count to 4 billion, counting one number per second without sleeping or stopping, it would take you about 127 years. And you'd only have counted 4 billion seconds, not 4 billion years. But from the perspective of the cosmos, 4 billion years is less than a third of cosmic history. Stars live for billions of years. Galaxies evolve over billions of years. The slow dance of the Milky Way and Andromeda is just one more process playing out on these vast timescales. And here's what's remarkable. We can predict this. Using the laws of physics discovered by humans over the past few centuries, using computers that didn't exist a few decades ago, we can simulate what will happen billions of years in the future. We can watch virtual galaxies collide and merge. We can see, in accelerated time, the transformation that will occur. This is the power of science. It allows us to see beyond our human timescales, to understand processes that unfold over periods far longer than human civilization has existed. We'll never see the Andromeda collision ourselves, but we can know what it will be like. We can understand our galaxy's future, even if we can't experience it. The approach continues, relentless and unstoppable. Every year, Andromeda gets a little closer. Every century, the gravitational pull grows a little stronger. Every million years, the distortions become a little more pronounced. The two galaxies are falling together like two drops of water merging on a window pane, drawn by forces they cannot resist. Let me describe what computer simulations show in more detail. These simulations are marvels of computational physics. They track the motions of millions, or billions of particles, each representing a clump of stars and dark matter. They calculate the gravitational force between every pair of particles, step by step, advancing the simulation forward in time. In these simulations, the approach looks deceptively gentle at first. Two spiral galaxies, beautiful and symmetric, orbit their common center of mass in the vast emptiness of space. They're far apart, barely interacting, just two bright pinwheels turning slowly in the dark. But as time passes, they draw closer. The simulations show the spirals beginning to distort, the outer arms reaching toward each other. Tidal bridges form, delicate filaments of stars stretching across the void. The cores of the galaxies remain distinct, still separated by enormous distance, but the outer regions are blending. The approach accelerates. The distance shrinks faster and faster as gravity's pull intensifies. The spirals elongate, stretching toward each other like taffy being pulled. Gas flows between the galaxies, heated by shock waves, glowing with the light of triggered star formation. And then, first contact. The outer edges interpenetrate, stars from one galaxy fly past stars from the other. The merger has begun, but first contact is just the beginning. The real drama unfolds over the next billion years as the collision transforms everything. Because what happens next reshapes both galaxies completely. But before we move on, let me leave you with one thought about the approach phase. Everything I've described, everything that will happen over the next 4 billion years, is already in motion. The gravitational forces are already acting. The acceleration is already occurring. Every day, every hour, every minute, Andromeda gets slightly closer. When you go outside tonight and look at that approaching galaxy in the sky, you're looking at your galaxy's probable future. You're looking at the object that will likely transform the Milky Way into something completely different. The encounter may be 4 to 5 billion years away, but the gravitational dance started the moment the two galaxies formed. It's been progressing ever since, and it will continue, driven by forces beyond any intervention, long after every human who ever lived has been forgotten. The approach isn't just something that will happen in the future, it's happening now. Let me tell you about other galaxy collisions we can observe, because they give us a preview of what's coming for the Milky Way and Andromeda. Across the universe, galaxy mergers are happening constantly. By observing them at different stages, astronomers have assembled a detailed picture of how collisions unfold. The Antennae galaxies, located about 60 million light-years away in the constellation Corvus, are one of the most studied examples. Two spiral galaxies similar in size to the Milky Way are in the process of merging. Long tidal tails extend from each galaxy, giving the system its name because they resemble insect antennae. The collision began about 300 million years ago. The two galaxies have already made one close pass and are falling back together for another. The region where the two galaxies overlap is filled with bright knots of star formation, thousands of new star clusters being born from compressed gas. When you look at images of the Antennae galaxies, you're looking at a preview of the Milky Way's future. The same gravitational forces are at work. The same tidal distortions are occurring. The same starburst activity is happening. In a few billion years, the Milky Way and Andromeda will look remarkably similar to what we see in the antennae today. The mice galaxies offer another perspective. These two spirals, located about 300 million light-years away, have made their first close pass and are moving apart before falling back together. Their long tidal tails really do resemble mice, with long tails chasing each other through space. The mice show us what happens between passes in a galaxy collision. Star formation has occurred during the first encounter, but now it's subsiding as the galaxies separate. When they fall back together, it will spike again. This cycle of interaction and separation can repeat multiple times before the final merger. NGC 2207 shows yet another stage. This system consists of two elliptical galaxies, the products of an earlier merger that are themselves now merging. It's a merger of mergers, demonstrating that this process can continue over cosmic time. Large galaxies grow by consuming smaller ones and merging with their peers. Perhaps the most famous merger remnant is Centaurus A, located about 12 million light-years away. This giant elliptical galaxy shows clear evidence of a recent merger. A dark dust lane cutting across its middle, the remnant of a spiral galaxy that fell in perhaps a few 100 million years ago. Jets of material shoot from its center, powered by its active, supermassive black hole. Centaurus A gives us a glimpse of what Milkomeda might look like a few 100 million years after the merger completes. The chaotic activity of the collision has settled down, but traces remain. The galaxy is still adjusting to its new structure. These observations, combined with computer simulations, allow astronomers to predict the Milky Way Andromeda collision with considerable confidence. We know the initial conditions, the masses, positions, and velocities of both galaxies. We know the physics, Newton's law of gravitation, supplemented by general relativity for the most extreme conditions. We can run the simulation forward in time and watch what happens. Different simulations using different methods give broadly consistent results. The galaxies will collide. They will undergo multiple passes. Star formation will spike during each close encounter. The spiral structure will be destroyed. An elliptical galaxy will result. The details vary depending on assumptions, but the overall picture is robust. There's something philosophical to consider here as well. The approach phase raises questions about the nature of change and permanence in the universe. The Milky Way seems eternal to us. It contains hundreds of billions of stars. It seems like the kind of thing that should last forever. But nothing lasts forever. Even galaxies are temporary structures, forms that arise and persist for billions of years, but eventually transform into something else. The Milky Way that we know, the beautiful spiral that humans have gazed at for thousands of years, is not permanent. It's a stage in a longer process, a form that arose from earlier cosmic evolution and will give way to later forms. This isn't sad, necessarily. It's just the nature of the universe. Change is constant. Everything flows. The Greek philosopher Heraclitus said you can't step in the same river twice because the waters have flowed on. In a similar way, you can't look at the same Milky Way twice. It's always changing, always evolving, always becoming something else. The Andromeda collision is just a more dramatic example of this constant change. Over the next 4 billion years, the change will accelerate. The slow, gradual evolution of the Milky Way will give way to a rapid transformation that reshapes everything. Stars that have orbited peacefully for billions of years will be flung onto new paths. Gas that has drifted through the interstellar medium will be compressed and transformed into new stars. And through it all, the laws of physics will remain constant. Gravity will continue to attract. Momentum will continue to be conserved. Energy will continue to be neither created nor destroyed. The collision will unfold according to principles that humans discovered centuries ago. Principles that govern everything from falling apples to merging galaxies. This is the profound lesson of the approach phase. The universe is comprehensible. The future is predictable, at least in its broad outlines. We may not be able to say exactly where any individual star will end up, but we can say with confidence what the overall outcome will be. We can watch the future unfold in our simulations, billions of years compressed into minutes of computer time. We know what's coming, the collision itself, the multiple passes, the burst of star formation, the destruction of both spiral structures, the chaotic transformation that follows. First contact is just the beginning. The real drama is yet to come. 4 billion years have passed. The approach is over. Andromeda is no longer a distant galaxy. It's here, interpenetrating the Milky Way. 2 vast islands of stars passing through each other in the most dramatic cosmic event we can predict. Let me be clear about what's happening. The word collision suggests a crash, an impact, a sudden violent event. But that's not quite right. Galaxy collisions are more like 2 swarms of bees passing through each other than like 2 cars crashing. The individual bees, or in this case stars, don't hit each other. They pass through the spaces between each other. But the swarms as a whole are profoundly transformed. When first contact occurs, around 4 to 4.5 billion years from now, the outer edges of both galaxies begin to interpenetrate. Stars that have spent billions of years in the Milky Way find themselves in regions also populated by stars from Andromeda. The two stellar populations begin to mix. This mixing happens first in the halos, those diffuse outer regions where stars are sparse. Here, the encounter is relatively gentle. Stars pass by each other at high speeds, hundreds of kilometers per second, but the distances between them remain enormous. The gravitational effects come not from individual stars, but from the collective mass of the approaching galaxy. But the cores are a different story. The cores of both galaxies are dense concentrations of stars and dark matter. As these cores approach each other, the gravitational effects intensify dramatically. The tidal forces that have been stretching both galaxies reach their maximum strength. Computer simulations show what happens next. The two galaxies don't simply merge smoothly. Instead, they pass through each other and swing out to a great distance before falling back together. This cosmic dance repeats multiple times, each pass transforming the galaxies further, before they finally merge into a single structure. Think of it like a gravitational yo-yo. The galaxies fall toward each other, pass through each other, and then their mutual gravity pulls them back. They fall together again, pass through again, and swing out again. Each pass takes hundreds of millions of years. Each pass scrambles the stars further, destroys more of the original structure, creates more new stars from compressed gas. The first pass is particularly dramatic. The two galaxies have been approaching for billions of years, building up tremendous kinetic energy. When they finally interpenetrate, they're moving at hundreds of kilometers per second relative to each other. Stars are flung onto wildly different orbits. Gas clouds collide at enormous speeds, shock waves propagating through the interstellar medium. During this first pass, the spiral structures of both galaxies are effectively destroyed. The beautiful pinwheel patterns that defined both galaxies for billions of years are torn apart by gravitational forces. The arms are stretched, twisted, and scattered. What was once an orderly spiral becomes a chaotic mess of stars on random orbits. The gas responds even more dramatically. Unlike stars, gas clouds can collide directly. When gas from the Milky Way meets gas from Andromeda at speeds of hundreds of kilometers per second, the result is catastrophic. The gas is heated to millions of degrees, creating vast shock waves that propagate through both galaxies. These shock waves do something remarkable. They compress the gas they pass through, and when gas is compressed sufficiently, it begins to collapse under its own gravity. New stars are born. The first pass triggers the most intense starburst the Milky Way has ever experienced. Star formation rates spike to perhaps 50 or 100 times their normal level. Regions that were dark and quiet for billions of years suddenly light up with the brilliance of newborn stars. The night sky, if anyone were there to see it, would be transformed. Many of these new stars are massive. When gas collapses rapidly during a starburst, it tends to form more massive stars than normal. These blue giants are incredibly luminous, outshining smaller stars by factors of thousands or millions. They also burn through their fuel quickly, living only a few million years before dying in supernova explosions. The supernovae add to the chaos. Each supernova releases as much energy in seconds as the sun produces over its entire lifetime. The explosion sends shockwaves through the surrounding gas, compressing it further, triggering even more star formation. It's a cascade, a chain reaction of stellar birth and death that transforms the merged galaxies. The first pass doesn't last forever. After perhaps 200 million years, the galaxies have passed through each other and are moving apart. For a brief cosmic moment, they separate, the distance between their cores growing. Someone watching from afar might think the collision was over, that the galaxies were going their separate ways. But gravity doesn't let go. The galaxies are bound together, their combined mass creating a gravitational well that neither can escape. As they move apart, their mutual attraction slows them, then stops them, then begins pulling them back together. The turnaround takes time. The galaxies might separate by several 100,000 light-years before falling back. This gives them perhaps a few 100 million years of relative calm, a brief respite before the next pass. Star formation continues at elevated levels, but the most intense activity of the first pass has subsided. Then the second pass begins. The galaxies fall together again, gathering speed as gravity accelerates them. By now, both galaxies are barely recognizable. The spiral structure is gone, replaced by irregular, chaotic shapes. Long tidal tails extend from each galaxy, streams of stars flung outward by the gravitational violence. The second pass is different from the first because the galaxies have already been transformed. The gas distribution has changed. Some gas was ejected during the first pass, flying outward along tidal tails. Some gas was consumed in star formation. Some gas was heated to such high temperatures that it expanded into a diffuse halo around the merged system. But there's still plenty of gas left, and the second pass compresses it again. Star formation spikes once more, though perhaps not as intensely as during the first pass. More massive stars are born. More supernovae explode. The cycle continues. The cores of the two galaxies are getting closer with each pass. During the first pass, the cores might have remained hundreds of thousands of light years apart, even at closest approach, passing through each other's outer regions without directly interacting. But with each subsequent pass, the cores lose orbital energy through a process called dynamical friction. Dynamical friction is a subtle but important effect. When a massive object moves through a field of other objects, it gravitationally attracts them, creating a wake of material behind it. This wake pulls backward on the moving object, slowing it down. It's similar to the drag a boat experiences moving through water, but caused by gravity rather than fluid friction. The cores of both galaxies experience dynamical friction as they move through the merged stellar system. Each time they pass each other, they lose a bit of orbital energy. Their orbits shrink. They get closer and closer to the center of the merged system. The supermassive black holes at the centers of both galaxies are along for the ride. Each black hole is embedded in a dense cluster of stars, the nucleus star cluster at the center of each original galaxy. As the cores approach each other, so do the black holes. But the black holes won't merge immediately. That process takes much longer, involving additional physics we'll explore shortly. For now, the black holes are just passengers, carried along as their host star clusters spiral toward each other through dynamical friction. Let me describe what a hypothetical observer might see during the collision. Imagine you're on a planet orbiting a star somewhere in the merged system. What would the sky look like? During the first pass, the sky would be extraordinary. Andromeda, which had been growing larger for billions of years, would now fill an enormous portion of the sky. But it wouldn't look like the smooth spiral of old photographs. It would be distorted, stretched, shot through with bright knots of star formation. The Milky Way's own band of light would be transformed as well. The familiar pattern that humans knew would be gone, replaced by irregular streaks and concentrations. New bright stars would appear in unexpected places, the products of collision-triggered star formation. The entire sky would be brighter than before. The combined light of triggered star formation and the merging of 2 galaxies worth of stars would increase the total background glow. True astronomical darkness would be hard to achieve. The night sky would always have a faint luminosity, the glow of a galaxy in transformation. During the quieter periods between passes, the sky would still be remarkable. Tidal tails would stretch across the heavens, rivers of stars arcing from one side of the sky to the other. Some regions would be unusually crowded with stars. Others would be surprisingly empty, areas where gravitational forces had swept the stars away. And every few 100 million years, the next pass would occur. The sky would light up with new star formation. Supernova explosions would become more frequent, sometimes visible to the naked eye, brief points of light that outshone everything else before fading away. Let's talk about what happens to the Sun and solar system during all this, because this is the question most people care about. Will Earth survive? The short answer is that the solar system will probably survive the collision intact. The gravitational binding between the Sun and its planets is far stronger than any tidal force the collision could produce. Even during the most intense gravitational interactions, the forces wouldn't be strong enough to rip the planets away from the Sun. But the Sun's orbit around the galactic center will change dramatically. Stars in the merged galaxy are scattered onto new orbits by gravitational interactions. The orderly circular orbits that stars follow in a spiral galaxy give way to more random elliptical orbits that plunge through the center of the merged system and back out again. The Sun might be flung outward, sent into the outer regions of the merged galaxy where stars are sparse. Or it might be sent inward, toward the dense central region where the black holes are spiraling together. Or it might end up on a stable orbit somewhere in between. There's no way to predict exactly where any individual star will end up. Simulation suggests there's a small probability, perhaps 10 to 20%, that the Sun will be ejected entirely from the merged galaxy. Gravitational interactions during the merger can accelerate stars to velocities greater than the escape velocity of the combined system. These stars fly off into intergalactic space, never to return. If the Sun were ejected, the solar system would go with it. The Earth and other planets would remain bound to the Sun, orbiting as they always have, but instead of being part of a galaxy surrounded by other stars, the solar system would become a lone wanderer in the vast emptiness between galaxies. From a planet in such a system, the night sky would be dark in a way we can barely imagine. Instead of the dense band of the Milky Way stretching overhead, there would be only the diffuse glow of distant galaxies. The nearest stars might be millions of light years away. The isolation would be absolute, but this outcome is unlikely. Most stars, including probably the Sun, will remain part of the merged galaxy. They'll just be on different orbits than before, scattered by the gravitational violence of the merger. The solar system itself will be unchanged. The distances between planets, the orbital periods, The fundamental structure of our star system are determined by the sun's gravity, not the galaxy's. Whether the sun is at the center of the merged galaxy or its outskirts, whether it's on a circular orbit or a plunging ellipse, the planets will continue their eternal dance around their parent star. Of course, there are other concerns for Earth 4 billion years from now. The sun is aging. In about 5 billion years, it will exhaust the hydrogen in its core and begin its transformation into a red giant. It will expand enormously, possibly engulfing Earth. Even before that, the increasing luminosity will have made Earth's surface inhospitable. The Andromeda collision is just one of many cosmic processes that will affect Earth's long-term future. In some ways, it's not the most threatening. The sun's evolution is more certain to affect Earth than the collision sun. But the collision is the most dramatic, the most visually spectacular, the most transformative for the galaxy as a whole. Let's return to the collision and follow it further. After multiple passes, each taking hundreds of millions of years, the two galaxies finally settle into a single structure. The cores, which have been spiraling toward each other through dynamical friction, merge. These separate identities of the Milky Way and Andromeda are lost. What remains is a single, larger galaxy. This process takes a long time. From first contact to final settling, the merger might span 1 to 2 billion years. During that time, the appearance of the merged system changes dramatically. It goes through phases that astronomers have observed in other merging galaxies throughout the universe. There's the first pass phase, when the galaxies still retain some semblance of their original structure but are clearly interacting. There's the starburst phase, when star formation peaks and the merged system blazes with the light of newborn stars. There's the disturbed phase, when the system is irregular and chaotic, neither spiral nor elliptical. And finally, there's the relaxation phase, when the system settles into a more regular shape. By the end of the merger, about 5 to 6 billion years from now, the system has become an elliptical galaxy. The spiral structure is gone forever. The new galaxy is a roughly spherical or ellipsoidal collection of stars, all orbiting the center on random paths. There's no rotation in the sense that spiral galaxies rotate. Instead, stars move in all directions, their random motions balancing against gravity to maintain the galaxy's shape. This is the death of the Milky Way as we know it. The beautiful spiral, with its sweeping arms and bright star-forming regions, is no more. In its place is an elliptical galaxy, a shape that astronomers sometimes call dead, because elliptical galaxies have usually stopped forming new stars. They've used up or expelled their gas, and now simply age, their stars growing older and redder as time passes. But the merged galaxy isn't dead yet when it first forms. There's still gas left over from the collision, and star formation continues at modest levels. The most intense starburst has passed, but new stars are still being born. The galaxy is settling, but not yet settled. During this settling phase, there's an incredible amount of energy being released. The gravitational potential energy of two separate galaxies is being converted into kinetic energy as stars scatter off each other, and then into heat as that kinetic energy is shared throughout the system. If you could somehow harvest this energy, it would be staggering in quantity. The supermassive black holes are also active during this period. Gas falling towards the center finds its way toward the black holes, feeding them and causing them to emit enormous amounts of radiation. The merged galaxy might appear as a quasar, one of the most luminous objects in the universe, powered by matter falling into the central black holes. Quasars are active galactic nuclei taken to the extreme. A single quasar can outshine its entire host galaxy, producing as much light as hundreds of billions of stars from a region smaller than our solar system. This light comes from the accretion disk around the black hole, superheated gas spiraling inward and releasing energy before crossing the event horizon. The Milky Way and Andromeda might not become a full-fledged quasar, but they'll certainly become more active than they are today. The Milky Way's supermassive black hole, Sagittarius A star, is currently quiet, not actively feeding on large amounts of gas. During the merger, this will change. Gas will flow toward the center, and the black hole will light up. The merger transforms everything. The number of stars increases as gas is converted to stars during the starburst phases. The distribution of stars changes from concentrated in a disk to spread throughout a spheroidal volume. The types of stars shift as massive blue giants born in the starburst die off and the remaining population ages. The chemical composition of the merged galaxy changes too. Massive stars that form during the starburst produce heavy elements through nuclear fusion and release them when they explode as supernovae. These heavy elements enrich the gas from which later generations of stars form. The merged galaxy will have a higher proportion of heavy elements than either original galaxy did. Let me give you a sense of the visual spectacle. Throughout the collision, the merged system would be one of the most remarkable sights in the universe. Long tidal tails stretching hundreds of thousands of light years, bright knots of star formation scattered throughout, shock waves visible in the emission from heated gas. The cores of the two galaxies, still distinct for much of the merger, glowing with the concentrated light of their central regions. Telescopes on distant planets in other galaxies, if any existed, would see our merger happening over millions of years. They would classify it first as an interacting pair, then as a merger, then as a disturbed galaxy, and finally as an elliptical. They would see the same phenomenon we observe in the antennae galaxies, the mice galaxies, and countless other merging systems throughout the universe. This is the remarkable thing about galaxy mergers. They're not unique to us. They're happening all the time, throughout the universe, and have been happening since galaxies first formed. What makes our merger special is that we're inside it. We're participants, not just observers. The collision also affects the local group as a whole. Remember, the Milky Way and Andromeda are the two dominant members of a small collection of galaxies. When they merge, the gravitational dynamics of the entire group change. The smaller galaxies of the local group will be affected by the merger. Some might be drawn into the merged galaxy, consumed as the giant grows larger. Others might be flung outward, ejected from the group entirely by gravitational interactions. The structure of our cosmic neighborhood will be transformed. The Triangulum galaxy, M33, is particularly interesting. It's the third largest galaxy in the local group, and it orbits somewhere between the Milky Way and Andromeda. Simulations suggest it might merge with the Milky Way-Andromeda system during or after the main collision, adding its 40 billion stars to the total. By the end of the merger, the local group will be dominated by a single, large elliptical galaxy where there were once two spirals. The merged galaxy will contain over 1.5 trillion stars, making it one of the larger galaxies in the local universe. it will have consumed or ejected most of the smaller galaxies that once orbited the Milky Way and Andromeda. This is the fate of many galaxy groups. Large galaxies grow by consuming smaller ones. They merge with other large galaxies when they encounter them. Over cosmic time, the universe's galaxies become fewer in number but larger in size as gravity draws them together. Let me conclude this part with a reflection on what the collision means. The Milky Way has existed for 13 billion years. It formed in the early universe, built up through mergers with smaller galaxies, and settled into the beautiful spiral we see today. Generations of stars have lived and died within it. Our sun was born from gas enriched by earlier supernovae. Life emerged on Earth because the Milky Way provided the right conditions. And now, that galaxy is going to transform into something else. The spiral structure that has defined it for billions of years will be destroyed. The orderly rotation will give way to random motion. The star formation that has continued for billions of years will spike and then decline as the gas is used up or expelled. This isn't the end of everything. The merged galaxy will continue to exist for trillions of years. Stars will shine, planets will orbit. Perhaps life will continue somewhere in the new galaxy, looking up at skies very different from ours, but no less beautiful. But it is the end of the Milky Way as we know it. The galaxy that has been our home, the cosmic structure that contains everything humans have ever experienced, will cease to exist in its current form. It will become part of something larger, something different, something new. But before we explore what emerges from the cosmic fire, let me describe in more detail the physics of what happens during these close passes. Because understanding the physics helps us appreciate the drama of what's occurring. When two galaxies approach each other, each one creates a gravitational potential well. Think of a potential well as a depression in space-time, a valley that objects roll into. Every galaxy sits at the bottom of its own potential well, held there by gravity. When two potential wells approach each other, they begin to merge. The combined well is deeper than either individual well. Objects that were sitting at the bottom of one well now find themselves on the slope of a much larger well. They begin to move, accelerated by the changing gravitational landscape. This is what happens to stars during a galaxy collision. They're not being pushed or pulled by any direct force. Instead, the gravitational potential around them is changing, and they're rolling down the slopes of the new potential landscape. Some roll inward, toward the center of the merged system. Some roll outward, flung to great distances. Some acquire enough energy to escape entirely. The randomization of stellar orbits is a key outcome of the collision. In a normal spiral galaxy like the Milky Way, stars orbit the galactic center in relatively orderly paths. Most stars in the disk move in roughly circular orbits, all going the same direction, like cars on a racetrack. After the collision, this order is destroyed. Stars end up on all kinds of orbits. Circular, elliptical, highly elongated, even retrograde. Some stars plunge through the center of the merged galaxy on orbits that take them far into the outskirts, before bringing them back. The ordered rotation gives way to random motion. This random motion is what gives elliptical galaxies their shape. In a spiral, stars rotate together, creating the disk. In an elliptical, stars move in all directions equally, creating a roughly spherical or ellipsoidal shape. The shape is maintained not by rotation but by the random motions of individual stars, like molecules in a gas maintaining the shape of a balloon. The energy involved in the collision is staggering. The kinetic energy of two galaxies approaching at hundreds of kilometers per second is immense. Where does this energy go? Some of it goes into gravitational binding energy as the two systems merge into one deeper potential well. Some goes into the kinetic energy of ejected stars, those that escape the merged system entirely. Some goes into heating the gas, raising its temperature to millions of degrees. Some goes into the energy of newly formed stars, created from compressed gas during the starburst. Energy is conserved, as it must be, but it's transformed from one form to another. The organized kinetic energy of two galaxies approaching becomes the randomized thermal motion of gas atoms and the random orbital motion of scattered stars. The role of gas in the collision deserves special attention. Gas makes up only a small fraction of a galaxy's mass, perhaps 10 to 15%, but it plays a disproportionately important role in determining what the collision looks like. Gas is dissipational. Unlike stars, which pass through each other without interacting, gas clouds can collide. When they do, the kinetic energy of their collision is converted to heat through shock waves. The gas radiates this heat away, losing energy. This allows gas to sink towards the centers of galaxies, collecting in the deepest parts of the gravitational potential well. During a galaxy collision, gas from both galaxies funnels towards the center of the merged system. This creates an enormous reservoir of material for star formation and for feeding the central black hole. The intense star formation and active galactic nuclei that accompany galaxy mergers are direct consequences of this gas concentration. The gas also determines where new stars form. Stars form from gas, not from other stars. In regions where gas is compressed by the collision, new stars appear. In regions that have been swept clean of gas, no new stars can form. The distribution of star formation during the merger reflects the distribution of gas and the pattern of compression. Understanding these physical processes helps us interpret what we see in colliding galaxies throughout the universe. The bright knots of star formation, the tidal tails, the distorted shapes, the active nuclei, all of these features have explanations rooted in the physics of gravity, gas dynamics, and stellar evolution. The Milky Way Andromeda collision will follow the same physics. We can predict its general features because we understand the underlying processes. The specific details, where exactly each star ends up, are unpredictable because the system is chaotic. But the overall outcome, if the collision occurs, is well understood because it's governed by physical laws we've tested throughout the universe. And now, let's see what emerges from the cosmic fire. The collision is over. 2 billion years of gravitational chaos have transformed the Milky Way and Andromeda into something entirely new. What remains is a single giant elliptical galaxy, born from the merger of two spirals, containing the combined stellar populations of both parent galaxies. Astronomers have given this future galaxy a name, Milkomeda, a portmanteau of its two progenitors. Some prefer Milkdromeda. Either way, it represents the final form of our cosmic home. Let me describe what Milkomeda looks like. Unlike the beautiful spiral structure of the Milky Way, Milkomeda is roughly spheroidal in shape. Think of a slightly flattened ball, like a hamburger bun or an oblate spheroid. Stars orbit the center in all directions, their paths random and elliptical rather than circular. There's no disk, no spiral arms, no clear structure beyond a gradual increase in stellar density toward the center. The color of Milkomeda is different from the color of its parent galaxies. The Milky Way and Andromeda, as spiral galaxies, contained a mix of young blue stars in their spiral arms and older red stars in their central bulges. The blue stars gave the spiral arms their characteristic color and brightness. But Milkomeda's blue stars are mostly gone. The massive stars born during the starburst phases of the collision have all died. These stars burn through their fuel quickly, living only millions of years rather than billions. By the time Milkomeda settles into its final form, the starburst is long over and the massive blue stars have all exploded as supernovae. What remains are lower mass stars that burn their fuel slowly. These stars are predominantly yellow, orange, and red. They'll shine for billions or even trillions of years, but they're not as bright or hot as the massive stars. Milkomeda appears redder and dimmer than either of its parent galaxies did in their prime. This is typical for elliptical galaxies. They're sometimes called red and dead because they're dominated by old red stars and have stopped forming new stars. Milkomeda fits this description, at least in its initial form. The gas that would be needed for star formation has been either consumed during the starburst, heated to such high temperatures that it can't collapse, or expelled from the galaxy entirely. The central region of Milkomeda is particularly interesting. This is where the cores of both original galaxies ended up, where the densest concentrations of stars now reside. The stellar density here is much higher than anywhere else in the galaxy. If you were on a planet in this region, the night sky would be ablaze with stars. You might see thousands of stars, as bright as Venus appears in our sky. True darkness would be impossible to achieve. And at the very center of Milkomeda, something extraordinary is happening. The two supermassive black holes, one from the Milky Way and one from Andromeda, are spiraling toward each other. This process takes much longer than the galaxy merger itself. While the stars settled into their new orbits relatively quickly, the black holes continue their dance for hundreds of millions or even billions of years after the main merger is complete. Let me explain why the black holes take so long to merge. When the two galaxies first collided, their supermassive black holes were embedded in the dense nuclear star clusters at each galaxy's center. As the galaxy cores merged, the black holes were brought closer together. But getting two black holes to actually merge is surprisingly difficult. At first, the black holes lose orbital energy through dynamical friction, the same process that brought the galaxy cores together. They scatter stars that pass near them, transferring orbital energy to those stars and sinking deeper into the center of the merged galaxy. This process works well when the black holes are far apart and there are plenty of stars to scatter. But as the black holes get closer, they run out of stars to scatter. The region between them becomes depleted of stars because any star that wanders close enough to be scattered gets ejected. This creates a problem. Without stars to scatter, the black holes can't lose orbital energy through dynamical friction. They get stuck in a binary orbit, circling each other but unable to get any closer. This is called the final parsec problem. A parsec is about 3.26 light years. When the black holes are separated by about a parsec, they've scattered all the stars in their vicinity and can no longer approach each other through dynamical friction alone. There are several possible solutions to this problem. One is the continued supply of new stars from the outer regions of the galaxy. Stellar orbits in an elliptical galaxy are chaotic, and some stars will wander into the central region on timescales of millions or billions of years. These stars can interact with the black hole binary and help it shrink further. Another solution involves gas. If there's still gas in the central region, it can form a disk around the black hole binary. This disk creates drag on the black holes, causing them to spiral inward. The gas also tends to make the black hole orbits more circular, which accelerates the inspiral. A third solution is gravitational radiation. Once the black holes are close enough, perhaps separated by about 1,000th of a parsec, they begin to emit gravitational waves. These ripples in space-time carry energy away from the system, causing the black holes to spiral inward faster and faster. Eventually, after perhaps hundreds of millions or billions of years, the black holes merge. This final merger happens rapidly. In the last fraction of a second, the black holes spiral together at a significant fraction of the speed of light, emitting more energy and gravitational waves than all the stars in the galaxy emit in light. It's one of the most violent events in the universe. The gravitational wave burst from this merger would be detectable by instruments throughout the observable universe, if any existed at that time. The LIGO and Virgo detectors that currently observe gravitational waves on Earth can detect black hole mergers billions of light years away. A merger of two supermassive black holes with masses in the millions or hundreds of millions of solar masses would be extraordinarily powerful. After the merger, Milkomeda has a single supermassive black hole at its center. This black hole has a mass roughly equal to the sum of the two original black holes, perhaps 100 to 150 million solar masses. It sits at the gravitational center of the galaxy, surrounded by the dense stellar core, slowly consuming any gas or stars that wander too close. Let's step back and consider the fate of our solar system in this new galaxy. By the time Milkomeda has settled into its final form, around 5 to 6 billion years from now, the Sun is in trouble anyway. It's nearing the end of its main sequence life. In about 5 billion years, the Sun will begin to transform into a red giant. The red giant phase will be dramatic. The Sun will exhaust the hydrogen in its core and begin fusing hydrogen in a shell surrounding the core. This causes the outer layers to expand enormously. The Sun will grow to perhaps 100 times its current diameter, engulfing Mercury and Venus. Whether it engulfs Earth is uncertain, depending on exactly how much the Sun expands and how much mass it loses during the expansion. Even if Earth survives, it will be uninhabitable. The expanded Sun will be close enough that its surface will fill a huge portion of the sky. The heat will boil away any remaining water and potentially melt the surface rocks. Earth, if it still exists, will be a barren, lifeless world. Eventually the Sun will shed its outer layers in a planetary nebula, leaving behind a white dwarf. This dense remnant, about the size of Earth but with a mass comparable to the current Sun, will slowly cool over trillions of years. The planets that survive, likely including Earth's orbit at least, will continue to orbit this dying ember. So the Andromeda collision doesn't directly kill Earth, the Sun does that on its own. But the collision does change where in the galaxy the solar system ends up. Remember, during the merger, stars are scattered onto new orbits. The Sun might end up in the outer regions of Milkomeda, far from the dense central core, or it might end up on an orbit that plunges through the center, taking it periodically through regions of high stellar density, or it might be ejected entirely, sent wandering through intergalactic space. As I mentioned earlier, there's a small chance the Sun will be ejected entirely. Most simulations suggest the Sun will remain part of the merged galaxy, just on a different orbit than it would have had in an undisturbed Milky Way. If the Sun remains in Milkomeda, its white dwarf remnant will eventually fade away. Over trillions of years, it will cool from white to yellow, to red, to infrared to microwave, eventually becoming invisible in all wavelengths. The solar system, by then a collection of cold, dark planets orbiting a cold, dark stellar remnant, will continue to exist, but will be utterly lifeless. If the Sun is ejected from Milkomeda, the outcome is similar but more isolated. The solar system will drift through intergalactic space, surrounded by nothing but distant galaxies visible as faint smudges of light. The isolation will be absolute, but ultimately irrelevant to a dead, frozen system. Let me describe the night sky from a planet in Milkomeda. It would be very different from Earth's sky today. First, there would be no Milky Way band stretching across the sky. The Milky Way's band is visible because we're inside a disc-shaped galaxy, looking along the plane of the disk. Milkomeda is not disc-shaped, it's roughly spherical. From inside such a galaxy, you see stars in all directions roughly equally. There's no band, no concentration in one part of the sky. Second, the night sky would likely be dimmer overall. Elliptical galaxies have lower surface brightness than spiral galaxies because their stars are spread through a larger volume. Unless you're in the dense central region, you might see fewer bright stars than we do on Earth. Third, there would be fewer bright blue stars. The massive stars that produce most of the blue light in a spiral galaxy are gone in an old elliptical. The stars you see would be predominantly yellow, orange, and red. Fourth, there would be fewer nebulae. The bright emission nebulae and reflection nebulae that decorate the Milky Way's spiral arms are associated with the regions of star formation. In Milkomeda, star formation has largely ceased. The beautiful clouds of gas and dust that we see in Earth's sky would be absent or much rarer. The overall impression would be of an older, quieter galaxy. Less dramatic than the Milky Way. More settled. The violent phase is over. What remains is a slow decline toward eventual darkness. Let's extend our gaze further into the future. What happens to Milkomeda over truly cosmic timescales? In the immediate aftermath of the merger, Milkomeda continues to evolve. Star formation persists at low levels for a while, fueled by whatever gas remains, but eventually the gas is used up or expelled, and star formation ceases entirely. No new stars are born. The galaxy contains only the stars it already has, plus whatever it acquires by consuming smaller satellite galaxies. Over billions of years, these stars age. The most massive stars die first, leaving behind neutron stars and stellar mass black holes. Medium mass stars like the Sun become white dwarfs. Only the smallest, coolest stars, the red dwarfs, continue to shine. Red dwarfs are remarkable objects. Red dwarf, with about 8% of the Sun's mass, burns its fuel so slowly that it can shine for trillions of years. Long after the Sun has become a cold, dark white dwarf, some red dwarfs will still be shining, still providing light and heat to any planets that orbit them. The universe is about 13.8 billion years old. Red dwarfs can live for 10 trillion years or more. That means no red dwarf has ever died of old age in the entire history of the universe. Every red dwarf that has ever formed is still shining today. They're the longest lived stars in the cosmos. In Milkomeda, red dwarfs will be the last stars shining. After all the other stars have become white dwarfs, neutron stars, or black holes, red dwarfs will continue their patient burning. The galaxy will grow dimmer and dimmer as the larger stars fade, but these small, cool stars will keep producing light for an almost incomprehensibly long time. But even red dwarfs eventually die. After 10 or 20 trillion years, the last red dwarfs will exhaust their fuel and fade. Milkomeda will contain no more shining stars. The only light will come from slowly cooling white dwarfs and the occasional flash of colliding compact objects. This period is called the degenerate era. The galaxy contains only degenerate matter, white dwarfs, neutron stars, and black holes. These objects don't generate energy through fusion like normal stars. They simply cool, releasing the heat they retained from earlier times. Over vast periods, they approach absolute zero. The universe during the degenerate era would be dark and cold. The background glow of distant galaxies would fade as they, too, entered this phase. The cosmic microwave background, the remnant heat from the Big Bang, would cool further as the universe expanded. Space itself would be barely above absolute zero. But even the degenerate era doesn't last forever. Over truly enormous timescales, much longer than the current age of the universe, even these objects decay. Protons might not be eternal. Some theories in physics predict that protons decay over timescales of perhaps 10 to the 36th years. If this is true, all matter made of protons and neutrons will eventually disintegrate. White dwarfs, neutron stars, planets, and any other surviving matter will slowly dissolve into radiation. Black holes themselves eventually evaporate through a process called Hawking radiation. Every black hole slowly emits particles, losing mass over time. For stellar mass black holes, this process takes about 10 to the 67th years. For supermassive black holes like the one at the center of Milkomeda, it takes perhaps 10 to the 100th years. These timescales are beyond comprehension. The current age of the universe, 13.8 billion years, is about 10 to the 10th years. We're talking about periods that are 10 to the 90th times longer than the current age of the universe. Numbers this large have no intuitive meaning. They're just symbols representing incomprehensibly vast stretches of time. Eventually, even the supermassive black hole at the center of Milkomeda will evaporate. The final burst of Hawking radiation will mark the end of the last concentrated object in what was once our galaxy. After that, there will be nothing left but diffuse radiation spreading through expanding space, growing ever colder and more dilute. This is the heat death of the universe, or at least of our corner of it. Maximum entropy. No more useful energy, no more structure, no more possibility of life or activity of any kind. Just radiation spreading through space forever. But let me step back from these remote futures and bring us back to something more immediate. The Andromeda collision teaches us something about our place in the universe. First, it teaches us that nothing is permanent. The Milky Way has existed for 13 billion years. It seems eternal on any human timescale, but it's not eternal. It will transform, cease to exist in its current form, become part of something else. This is the fate of all structures in the universe. Everything changes. Everything flows. Second, it teaches us that we can predict the future. Using the laws of physics that humans discovered over the past few centuries, using computers that didn't exist a few decades ago, we can simulate events that may happen billions of years from now. We can glimpse possible futures. Not perfectly, not in every detail, but in broad outline. The Andromeda encounter will occur in some form. Some version of Milkomeda will likely form. These predictions, while not absolute certainties, represent our best understanding of cosmic evolution. Third, it teaches us perspective. Human concerns, human conflicts, human achievements, all of it plays out against a cosmic backdrop of unimaginable scale and duration. The Milky Way doesn't care about human politics or economics or wars. It's going to collide with Andromeda regardless of what happens on Earth. Our galaxy's fate was determined by gravity billions of years ago, long before Earth existed. This isn't meant to diminish human concerns. Our lives matter to us, and that's enough. But cosmic perspective can help us see our lives in a broader context. It can remind us that we're part of something vast and ancient, that our existence is a brief flicker in a cosmic story that spans billions of years. Fourth, it teaches us that we're connected to the universe. The atoms in your body were forged in stars that died billions of years ago. The elements that make up Earth came from supernovae, from neutron star mergers, from the nuclear fires of stellar cores. We're made of star stuff, as Carl Sagan famously said, and that star stuff will eventually become part of Milkomeda, scattered through a galaxy that doesn't yet exist. Let me conclude with a thought experiment. Imagine you could travel in time to witness the collision. What would you want to see? Perhaps you want to see the first pass when the two galaxies interpenetrate for the first time. The sky would be ablaze with star formation. New stars would be appearing everywhere. Brilliant blue giants born from compressed gas. Supernovae would be common, visible as new stars that brightened and faded over weeks. The sky would never be the same from night to night. Perhaps you'd want to see the merger of the supermassive black holes. The gravitational waves from this event would be the most powerful ever detected, ripples in space-time propagating outward at the speed of light. If you could somehow perceive gravitational waves, this event would be deafening. Perhaps you'd want to see Milkomeda in its prime, after the merger has completed, but before the stars have faded. A giant elliptical galaxy, red and orange with old stars, dominated by the glow of its dense, central region. The tidal tails would have faded by then, absorbed back into the galaxy. The scars of the collision would be healed. What remained would be a stable, peaceful galaxy settling into its final form. Or perhaps you'd want to see the far future, when the last red dwarfs are flickering out and the universe is entering its final darkness. This would be the most profound sight of all, the end of everything, the final act in the cosmic drama. Not a bang, but a whimper, as T.S. Eliot might say. The slow fade into eternal night. We can't travel in time, we can't witness these events, but we can know about them, we can understand them, we can imagine them, based on the solid foundation of physics and astronomy. That's the gift that science gives us, the ability to see beyond our own brief existence, to understand processes that span billions of years. The Andromeda collision is already happening. The gravitational forces are already at work. Every second, the two galaxies draw slightly closer. Every year, the countdown advances. We're passengers on this journey, inhabitants of a galaxy that's falling toward its destiny. Tonight, when you look up at the sky, try to find Andromeda. It's visible as a faint fuzzy patch in the constellation Andromeda, northeast of the Great Square of Pegasus. You'll need dark skies, away from city lights, and some patience. But if you find it, you'll be looking at something remarkable. That faint glow contains more stars than the Milky Way. It's 2.5 million light years away. and it's heading toward us at 250,000 miles per hour. The light entering your eyes tonight left Andromeda 2.5 million years ago. When that light began its journey, our ancestors were just beginning to use stone tools. The entire history of the genus Homo has unfolded during the time it took that light to reach us. And during all that time, Andromeda has been getting closer. It was getting closer when the first humans walked upright. It was getting closer when we discovered fire, invented language, created art. It was getting closer during the rise and fall of every civilization. It was getting closer last night, and it will be getting closer tomorrow night. The countdown began billions of years ago. It will continue for billions of years more. But make no mistake, the final countdown is underway. The collision is coming, and when it arrives, the Milky Way as we know it will be gone forever. In its place will be Milkomeda, a new galaxy born from cosmic collision, containing the stellar legacy of both its parents. It will be home to whatever remains of our solar system, our planet, our memory. If anyone is there to remember, the universe is vast, ancient, and indifferent to our concerns, but it's also comprehensible. We can understand it. We can predict its future. We can know what's coming. And what's coming 4 billion years from now is the transformation of everything we know. The end of the Milky Way. The beginning of something new. The final countdown continues tonight, as it has for billions of years, as it will for billions more. Good night. And remember, when you look at Andromeda, you're looking at our galaxy's most likely future. The gravitational forces drawing us together have been at work for billions of years. Whether we collide directly, graze past each other, or merge over eons, our cosmic neighborhood will never be the same. The Milky Way will change. Andromeda will change. And from their encounter, something new will emerge. This is the final countdown, and it's already underway. Let me leave you with some final thoughts about what this collision means for our understanding of the universe and our place in it. The Andromeda collision reminds us that we live in a dynamic universe. Nothing is static. Everything is moving, changing, evolving. Galaxies form from collapsing gas clouds, leave for billions of years, merge with other galaxies, and eventually fade into darkness. Stars are born, shine for millions or billions of years, and die. Planets form, exist for a time, and are eventually consumed or destroyed. Against this backdrop of constant change, human civilization is the briefest flicker. We've existed for perhaps 10,000 years in our current form, a span of time so short that the universe hasn't noticeably changed during it. The Milky Way looks the same today as it did when the first cities were built. Andromeda occupies the same patch of sky it occupied when humans first looked up and wondered about the stars. But on longer time scales, everything changes. The gravitational encounter that will reshape the Milky Way is already in progress. The forces are already at work. The trajectory is set, even if the exact outcome remains uncertain. We just won't be around to see it. Some people find this perspective disturbing. The vastness of space and time can seem to diminish human significance. If galaxies live for billions of years and humans for mere decades, what does our existence matter? I think this perspective is mistaken. Our significance doesn't depend on our duration. A beautiful sunset isn't less beautiful because it lasts only minutes. A meaningful conversation isn't less meaningful because it lasts only hours. Our lives aren't less valuable because they're brief by cosmic standards. What makes humans remarkable is not our longevity but our awareness. We're the universe becoming conscious of itself. Through us, matter has arranged itself in ways that can contemplate its own existence, can understand the laws that govern its behavior, can predict its own future. That's extraordinary, regardless of how long it lasts. The Andromeda collision is a perfect example. The collision itself will unfold over billions of years, completely indifferent to whether anyone observes it. But right now, in this brief window of cosmic time, conscious beings exist who can understand what's coming. We can simulate it, predict it, visualize it. We can know our galaxy's fate. This knowledge doesn't change the physics. The gravitational forces will continue whether we understand them or not. But the knowledge matters to us. It connects us to the larger universe. It helps us see our place in the cosmic story. Consider what it would be like to be a conscious being in Milkomeda, billions of years from now. If such beings exist, they'll live in an elliptical galaxy, surrounded by old red stars with no spiral arms and no Milky Way band stretching across the sky. They might know, from their own scientific investigations, that their galaxy was formed from the merger of two spirals. They might be able to trace the history back, to understand how the collision unfolded, but they won't know about us. Any record of human existence will be long gone, destroyed by the sun's expansion into a red giant, or simply lost to the ravages of time. Our civilizations, our art, our science, our love, all of it will be forgotten. Does that matter? Perhaps not. Our lives have value to us here and now, regardless of whether future beings remember us. The meaning we find in our existence doesn't depend on being remembered forever. It depends on how we live, how we treat each other, what we create and discover and experience. The universe will go on without us. The collision will happen. Milkomeda will form. Eventually, even Milkomeda will fade into darkness as its stars die. This is the nature of things. Everything that has a beginning has an end, but we get to be here for this particular moment. We get to be aware. We get to wonder and discover and understand. We get to look up at Andromeda tonight and know what's coming. That's something. That's a lot, actually. The final countdown is underway. It began billions of years ago, and it will continue for billions more. We won't see the end, but we can know about it. We can understand it. We can appreciate the vast cosmic drama of which we're a tiny part. And when you go outside tonight and look up at that pale glow in the constellation Andromeda, remember what you're seeing. You're seeing 1 trillion stars, 2.5 million light years away, heading toward us at 250,000 miles per hour. You're seeing our destiny. You're seeing the future of the Milky Way. You're seeing the beginning of the end, which is also the beginning of something new. The final countdown continues. It continues tonight, as it has every night since the universe began. And it will continue tomorrow night, and the night after, and every night for billions of years to come. Watch the sky. Witness the cosmos. Understand what you can while you can. That's all any of us can do. That's all any conscious being, anywhere in the universe, can do. Good night. Sleep well. And remember, the universe is vast, ancient, and astonishing. The Andromeda collision is just one small part of its endless story. But it's our part. It's the part that includes us. That makes it special. That makes it ours. That makes it worth understanding. The final countdown is underway.